Hi, welcome to this video in linear programming duality. This video is on the proof of strong duality. Strong duality is the feature of linear programming we introduced in the previous video in order to help us determine the remainder of this chart. This chart, which indicates the possible and impossible outcomes for a primal-dual pair of linear programs, was first introduced when we discussed weak duality. And weak duality allowed us to determine 2/3 of this chart. But there were still 3 cells that had not yet been determined using weak duality alone, namely the bottom left, bottom right, and top right cells. They had still gone unfilled to that point. So in the previous video, what we did was, at the end of it, we gave an explicit example which indicated that there do exist primal-dual pairs of linear programs where both the primal and the dual are both infeasible. And so correspondingly, we placed a green check mark in this bottom right cell to indicate that that was a possible outcome. And then we also introduced the statement of strong duality, which implied that there do not exist primal-dual pairs of linear programs where one is optimal and the other is infeasible. That's impossible, and so correspondingly, we placed red X's in the top right and bottom left cells symmetrically, because those could not happen. So now in this video, we are going to prove this statement of strong duality, which allowed us to fill out the remainder of this chart. Just as a heads up, before we get into the proof of strong duality, this will rely on features of linear programming that are outside the scope of duality itself, namely the simplex algorithm and canonical forms of linear programs. So if you're not comfortable with these topics already, it would likely be too difficult to follow this proof. So it would be best to skip this video for now and come back at a time when you're more comfortable with those topics. This will not hamper your understanding of future videos in the topic of duality. We will not reference the proof in the future. We will only need the statement itself. So as long as you're comfortable with the statement, that's good enough. This is simply for completion's sake to give the proof. However, I will go through a sketch of the proof if you're curious, just a light overview to get a vague idea of what's going on. It's also a strategy for the details of the proof as well, so it's useful either way, whether you're watching the full proof or not. But anyways, if you're curious about that, stick around for just a minute or two and we'll get into that. And then we'll go through the proof itself. So, just as a reminder, before we get into the proof, what is the statement of strong duality saying? So the setting is this. So let P and D be a primal-dual pair. So P is the primal, D is the dual. And the statement is the following. So if the primal has an optimal solution, then the dual does as well. So if the primal is optimal, the dual is also optimal, and moreover, the optimal solution for the primal and the dual will be equal in value. That is, when you plug the optimal solutions in, the values that come out to be will be the same, in fact. Okay, so this is the statement we're going to be proving. So there's 2 statements to prove there, really, but in fact what's going to happen is that both statements will be proved simultaneously. So let's see what the sketch of the proof of strong duality is before going through the details. So first what we're going to do is we're going to assume, without loss of generality, that the primal is in standard equality form. We can make this assumption because every linear program is equivalent to one in standard equality form, so in particular our primal will be. And equivalent primal linear programs will give rise to equivalent dual linear programs, so it doesn't hurt anything to assume that our primal is already in standard equality form. Now, why would we want our primal to be in standard equality form? Well, because next what we're going to do is we're going to run the simplex algorithm on the primal. And the simplex algorithm plays well with the standard equality form of a linear program, but not so much with other formats of the linear program. So you want to make sure that when you're using the simplex algorithm, which is what we're going to do, you want to make sure that your linear program is in standard equality form. So that's why we assume this, and now we run the simplex algorithm on the primal, and what this will do is this will give us an optimal solution x bar for an optimal basis b. Okay, so we know by hypothesis that the primal has an optimal solution. That's our hypothesis. So the simplex algorithm necessarily will find an optimal solution x bar. And in fact, so this will always be a basic feasible solution, and it will be the basic feasible solution corresponding to some basis b. And so that's the name of the basis that this is the basic feasible solution of. Okay, so now that we have this, we have an optimal solution for the primal. And so what we're going to do is we're going to rewrite the primal in canonical form for the basis b. And what this is going to allow us to do is, it's not obvious how this will work, but this is what's going to happen, is once we're in canonical form for the basis b, we're going to find a feasible solution y bar to the dual, thanks to being in canonical form for the primal. So that gives us a feasible solution y bar to the dual, and then we're going to use weak duality to show that that solution y bar is in fact optimal for the dual. And we will have a primal-dual pair of optimal solutions for the primal and the dual, and they will be equal to each other when we plug them into their objective functions, and this will imply the result. So the conclusion will follow. So we will be using weak duality in order to prove strong duality. Okay, so that's the sketch of this. So let's actually go through the details now and flesh all these concepts out. Okay, so here we go then. So so proof. So first of all, what we want to do is we want to assume, without loss of generality, the primal is in standard equality form. So let's write down our primal in standard equality form. So that means we're going to be maximizing a linear objective function C transpose X such that AX equals B and X is greater than or equal to 0. So I put this bar down to 0 to indicate this is a 0 vector, not just the number 0. So anyways, this is the format of standard equality form. We're maximizing a linear objective function subject to matrix equality constraints and variable non-negativity constraints. So that's standard equality form. So this is the primal, so that's parentheses P there. So let's write down the dual before we go any further. So what will the dual of this linear program be? Well, we already know what the dual format is. It will be B transpose Y such that A transpose Y is greater than or equal to C, and the Y variables will all be free. Okay, so B transpose Y, it's this vector B times the dual variables Y, and we're minimizing that upper bound such that these constraints, so we have a greater than or equal to constraint here corresponding to the variable non-negativity constraints in the primal, and then the matrix equality constraints in the primal give free variables in the dual. Okay, so this is the dual here. And so now we have the primal dual. So now let's keep going with the sketch here. So the next step is to run the simplex algorithm on the primal, and this will give us an optimal solution. Okay, so let's just write this down. So we'll run simplex algo on the primal. Okay, and what this will do is this will produce X bar, an optimal solution. Okay, and in fact, it's not just an optimal solution. This will be a basic feasible solution. Basic feasible solution for basis B. Okay, so that's what happens, and so we know this is going to happen because our primal by hypothesis has an optimal solution. So when you run the simplex algorithm, you will find an optimal solution, and so this X bar here, let me just clean that X up a little bit, X bar. So this X bar here will be able to be obtained. There will be some optimal solution that will be able to be obtained by the simplex algorithm, and that optimal solution will be a basic feasible solution as well. So, and here's the basis that it's a basic feasible solution for. The basis is B. Okay, so now we have our X bar optimal solution for the primal. So what's the next thing the sketch says? We're going to rewrite the primal in canonical form for the basis B. So if we were explicitly running the simplex algorithm, this would have automatically happened. That's part of the algorithm, but we're just imagining that this has happened, so we don't actually see the current state of the linear program P. So let's explicitly write it ourselves. So, so what we can do is, so what happens when you go into canonical form for various bases is that the linear program does not change at all in terms of the fundamental linear program. It is only the format that changes. And I mean, it's literally the exact same linear program. It's the exact same constraints and the exact same objective function, but it has been reformatted. So it's not even an equivalent linear program. It is the same linear program, but it is reformatted. So that's what happens when you go into canonical form for various bases. So, so what is the canonical form for this basis B then? Well, let's write it down below. Okay, so what it will be is we will be, so let me just say canonical form for the basis B is the following. So we'll be maximizing y bar transpose b plus c bar transpose x. Don't worry about what y bar and c bar are quite yet. I'll explain that in just a moment. Such that we have the following constraints. We'll have a b inverse times a x equals a b inverse little b, and also x greater than or equal to 0. Okay, so this is canonical form for the basis b, and so we'll label this p prime. Okay, so p prime down here is exactly the same linear program as p, despite appearances. It is the same in every way except the format. The format is the only thing that has changed. But the constraints and the objective function are identical. Okay, so actually what is y bar and c bar? We haven't completed this unless we know what these things are. So when you're in canonical form, this y bar is going to be, so we'll say where y bar equals ab inverse transpose c sub b, and c bar equals c minus a transpose y. Y bar. Okay, so y bar is given here, and then that y bar is used to determine c bar. So hopefully you're familiar with all this notation. So AB is indicating the submatrix of A indexed by the indices of the basis B, and that's an invertible matrix. And so this is the inverse of that matrix here that appears here, and then the inverse transpose appears here for this vector y bar, and then C sub B, those are the components of the coefficient vector C that are indexed by the basic indices as well. So for the basic indices, you pick those out, and that gives you this subvector C, and this product gives you the vector y bar, and then that y bar is used to give us c bar as well, and then that c bar appears here in the objective function. Okay, now why are we doing this? Well, what's happened as a result of being in a canonical form here and having terminated? Because when we're in this basis, what happened is this was the basis where we found our optimal solution. We found our basic feasible solution that was optimal, this x bar here. So the simplex algorithm terminated at this basis. So what does it mean for the simplex algorithm to have terminated here? So simplex terminated at basis B. Okay, so in order for that to happen, it terminated because it found our optimal solution. What that means is that this implies that c bar is less than or equal to 0, the 0 vector. So c bar, that's the current coefficients that appear in front of the C transpose x part. There's also plus this constant here. But as far as the C transpose x part, now it's C bar transpose x, but these are the coefficients that appear in front of the x's, and all of those are less than or equal to 0. Why is that true? Because what is the simplex algorithm doing? Well, what it does is it's trying to find positive coefficients in front of the x's so that it can boost the associated variable that's associated to that positive coefficient. But if it terminated, that meant it couldn't find any positive coefficients, and so all the coefficients had to be less than or equal to 0 then. So the c bar, those coefficients, had to be less than or equal to 0. That's the only way for simplex to have terminated, but it did terminate because this is where it found our optimal solution, x bar. Okay, so this must mean that c bar was less than or equal to 0, and what is c bar? Well, we can replace c bar. We know what c bar is. It's c minus a transpose y bar. So c minus a transpose y bar is less than or equal to 0, or in other words, c is less than or equal to a transpose y bar. Okay, and so this will complete the next step of our sketch. So what you see here is a transpose y bar is greater than or equal to c, if you read this backwards. So let's go back up to the dual now. You see in the dual, that was the constraint that we had, that a transpose y needed to be greater than or equal to c. So whatever vector y you found, it had to be the case that a transpose y was greater than or equal to c, and y bar down below is a specific vector that does satisfy that. So y bar is feasible for the dual. And okay, so that completes these first three steps then. We've rewritten the primal and canonical form for the basis in order to find a feasible solution y bar to the dual. We just showed that y bar is feasible. So let me just check off these first three steps here because we've done those things. And then finally, we're going to use weak duality to show that y bar is optimal for the dual, and the conclusion will follow. So let's come back down here and finish this off now. So, okay, so here we see that A transpose y bar is greater than or equal to C, so this implies y bar is feasible for the dual. Okay, great. So finally, what we're going to do is we're going to use weak duality. Now again, as I've mentioned, so here, this right here, P prime, this is canonical form for the basis B of our initial linear program P, and then P, just plain old P right here, was the initial formulation of that same exact linear program. And I mean they're exactly the same. So when you plug in a particular solution to the objective function here, that is the same as plugging in that same solution to the objective function in P prime as well. So here is P prime, and we can plug a solution into there. So let's plug in our optimal solution. Okay, so what we'll do is we'll plug in x bar to P. Okay, so this gives us C transpose x bar. Now this is going to be equal to what would happen if we plugged in x bar into P prime instead. So let me just put an arrow here. So this is same as plugging x bar into P prime. Since they are the exact same linear program, they are just simply reformatted. When I say reformatted, it's like the difference between 4/6 and 2/3. Those are the same fraction, they're just different formats. Okay, anyways, so C transpose x bar, this is equal then to y bar transpose B plus C bar transpose x bar. Okay, so what I did is, if I just come back right here, here is our objective function for P prime, and we're just plugging x bar into this. So y bar transpose B plus C bar transpose x bar now. It's the specific solution x bar. Okay, and now what we do is, so let me just write this as B transpose y bar instead. And now we're going to break this product into the basic and non-basic components. So the basic components are the components picked out by the basis B, and the non-basic components are all the rest. So we'll split it up like that. So C bar transpose B times x bar sub B plus C bar transpose n times x bar n. Okay, so these are the basic components, and these are the non-basic components, and when you take the dot product of everything, that gives you the dot product of the overall vector C bar transpose x bar. So we've just rewritten it in terms of splitting it up into basic and non-basic components separately. And why do we do that? Well, because part of what it means to be in canonical form for a basis is that it means that the coefficients in the canonical form for the basis B are zeros, okay? These are zeros. Let me just say equal to 0. So C bar sub B equals the 0 vector of the appropriate dimension. And that is because that's what it means to be in canonical form for the basis B. It means that those coefficients are all zeros. And then, for the non-basic components, we know that x bar is a basic feasible solution. It's the basic feasible solution for the basis B. And so that means that x bar sub n equals the 0 vector as well, again, of the appropriate dimension for the number of non-basic components. Okay, so why is C bar sub B equal to 0? We're in canonical form for the basis B. So that's why C bar sub B is equal to 0. And why is x bar sub n equal to 0? It's because x bar is the basic feasible solution for the basis B. So this is part of what it means to be a basic feasible solution. It means that the non-basic components are all zeros, and this is what it means to be in canonical form, or it's part of what it means to be in canonical form, that the coefficients for the basic components are all zeros. So anyways, the point of all this is to say that no matter whether we're in the basic part or the non-basic part, there's always zeros. We're always multiplying by zeros. For the basic components, it's the c's that are zeros. For the non-basic components, it's the x's that are zeros. But always there's a zero there that's getting multiplied, so this entire thing just vanishes. So in other words, c bar transpose x bar equals 0. So this all goes away. And we're just left with this part right here, which is b transpose y bar. So this all equals b transpose y bar. Okay, and so what that says then is that c transpose x bar equals b transpose y bar. So therefore, c transpose x bar equals b transpose y bar. And if you remember from above, what the dual linear program is it's minimizing b transpose y. So y bar is a particular solution which in which it's equal to c transpose x bar. Okay, so I can just go up really quickly here, and you can see here is the dual. The dual is right here, and it's b transpose y, and y bar is a specific solution that's getting plugged in there. And okay, so since c transpose x bar equals b transpose y bar, so I'll say therefore again, we'll say by weak duality, this implies that x bar and y bar are a primal-dual optimal pair. That is, x bar is an optimal solution for the primal. That was what we already knew from the start, and we just have now shown by weak duality that y bar is an optimal solution for the dual, since it is the case that c transpose x bar equals b transpose y bar. Okay, and so that's it then, because what you can see is that here on the left, this is the optimal value of the primal, and here on the right, this is the optimal value of the dual. And so therefore, the optimal value of the primal and dual are equal to each other. That came for free since weak duality showed that these were optimal, and then we see here that they're also equal to each other, and so we have the conclusion that we wanted. So that finishes the proof of strong duality. So I'll just go to the top one more time, just so you can see what the statement was supposed to be again. So strong duality statement is saying that for a primal-dual pair, if the primal has an optimal solution, that's what we assumed, then the dual does too. And that's what that y bar vector is. And moreover, those values are equal to each other because by weak duality, we just showed that they were equal to each other. They were equal to each other, so by weak duality, we showed that they were optimal to each other, and so then those optimal solutions then are equal to each other. So that's why, and that proves the statement of strong duality. Okay, so that's it then for this video. So thank you for watching.